So, welcome to this course on linear algebra. First, I want to give a little introduction. We will be dealing with vector spaces and linear maps among them. As you are aware, the origin of the concept vectors is most notably in physics and clearly described and developed in the geometry of real 3 space, which I keep calling the universe that we live in. Today, in general, we understand a vector is an element of a vector space. In this sense, the concept of vectors and vector spaces plays a fundamental role in all branches of mathematics, science as well as engineering. We will start this course with the abstract standpoint and conveniently pass on to geometric thinking. Moreover, such geometric perceptions are also beneficial in the framework of abstract theory. Foundations of geometry are most efficiently formulated in terms of the algebraic structures inherent in the geometry. It motivates drawing suitable pictures and is the source of inspiration for proving general results. With this, in the first half today, I would like to introduce abstract vector spaces. But before that, I would like to point out what prerequisites that one will need for this course and what exactly we will study in the whole course. So, first the prerequisites. I will assume that all of you are familiar with set theory, especially concepts of sets, maps and various operations on the sets and subsets. I also will assume that you are familiar with number systems, natural numbers, integers, rational numbers, real numbers, complex numbers and the standard natural operations of addition and multiplication on them. These systems I will keep denoting by n plus dot. This will be for the set of natural numbers, and I will also remind you that in the natural numbers I would like to add 0 as a natural number. In general, some books or some references it is not added usually, but I will insist that 0 is a natural number. Integers I will denote by z plus dot. These are integers. Then rational numbers q plus dot, real numbers dot and c plus dot. These are the real numbers and complex number systems. These plus and dot, they are the usual additions and multiplications on these sets, and I will assume that all of you are familiar with these number systems and their basic properties. In any case, if some properties are needed specifically, I will mention it at the time when we need it. And I will also assume that you are familiar with the basic concepts of the calculus. With this, I would like to start linear algebra and say that we are going to study of vector spaces and the algebra of linear operators on vector spaces. Usually one studies vector spaces over real numbers, but I am going to study over arbitrary fields. This is because in the present day applications of linear algebra is more important even for the case of finite fields. And to define the first half, I will define abstract vector spaces, and for that I will need concept of a field. So I would like to recall what are fields. These fields, so to define a vector space we need a field. And these fields are also called a scalar field of that vector space. So already the familiar examples, as I mentioned, among the number system, that you are probably aware that q plus dot, these form a field, or real, this is called a field of rational numbers. And r plus dot, this is a field of real numbers. Then C complex numbers is called field of complex numbers. In addition to these fields, I will also would like to recall what is a finite field, finite fields. So to recall this, I will go on to recalling the concepts of binary operation first. So a definition. So this the idea of this definition is to make things more general and also develop some notation which we will be using throughout the course, throughout this course. So a binary operation on a set G is a map from the product set G cross G to G. The image of an ordered pair x comma y under this map I will keep denoting just by xy and maybe call it a product of xy. Our standard notation sometimes will be the addition notation x plus y. This will be called additive notation. And this earlier will be called a multiplicative notation. So such a map is called a binary operation. We will say binary operation is commutative if x times y equal to y times x for all x and y in G. As you are aware that the natural addition and multiplication operations on the number systems are commutative. Further we will say that the operation is associative if x times yz bracket is equal to xy times z for all xy z in G. So this means this is a very important property that we need it all the time, because it is independent of the bracket we put it, and therefore it is very important for the calculation purpose. Okay. Further we will say that an element E in G is a neutral element if E times x equal to x times E equal to x for all x is g. Then such an element is called a neutral element, or also it is called identity element. For example, 0 is the identity element in the set of natural numbers, and it is also additive neutral element in the integers, also rational numbers, real numbers, complex numbers, and so on. 1 is the multiplicative neutral element in natural numbers, integers, rational numbers, real numbers, and complex numbers. These you have been seeing from the school days. Also, if I use multiplicative notation, usually I will denote the neutral element by 1g or eg in general. In case of multiplicative notation, I will denote it by 1g. In case of additive notation, I will denote it by 0g or simply 0 when there is no chance of any confusion. Immediately after the definition, I would like to show you that the neutral element, if it exists, it has to be uniqueness. For the uniqueness, we need to assume that the operation is associative. Suppose E and E prime are two neutral elements, then in G are two neutral elements, then E prime equal to E prime times E, which is E prime on one hand it is E prime because it's E prime, E is a neutral element. On the other hand, it is E because E prime is the identity, a neutral element. See, E prime equal to E prime E because E is the identity, E is the neutral element, and because E prime is the neutral element, E prime times E equal to E. So E equal to E prime. So that shows that if neutral element exists, it is unique. Okay, next we will call G a group. G is called a group. If the binary operation of G is associative to E exists, neutral element exists, and 3, every element of G, x in G, has inverse. That means there exists an element x prime in G with x times x prime equal to E, also equal to x prime times x. If such a x prime exists, then that element x prime is called the inverse of G, inverse of x prime is called inverse of x, and check that such a x prime is unique. In the multiplicative notation, this x prime is usually denoted by x inverse. In the additive notation, it is denoted by minus x. So G with the binary operation with these three properties is called a group. If only first two properties are satisfied, then it is just called a monoid. If only 1 and 2 are satisfied, then it is called a monoid. A typical example of a monoid prototype of a monoid is n plus n dot or z dot. These are just monoids and they are no groups. These are monoids, they are but not groups. Another example we will need later is the set of maps from X to X. This is the set of all maps from the set X into X. And the binary operation here is the composition. The circle is denoted as the composition of maps. This is a monoid and all elements of this monoid are not invertible. This monoid is also not in general commutative, not commutative in general. Okay. From the last monoid we can actually construct a group, or we can extract a group, namely the set of all, not all, but set of all bijective maps from X to X. This is the set of all bijective maps from X to X, from X onto X. In the notation I will write sigma from X to X. Sigma is bijective. Bijective means injective and surjective. Injective means different elements have different images, and surjective means everybody in X is in the image of sigma. So surjective means image of sigma, which is sigma X is X, and injective means if X is not equal to Y, then sigma X is not equal to sigma Y. I will keep using these terms all the time without any reference. So this is precisely, in fact, Sx is precisely all, this is the set of all invertible elements in the monoid x power x. So that is sigma belong to x power x, sigma is invertible with respect to composition in x power x. This simply means there exists a tau in x power x such that sigma compose tau equal to tau compose sigma, which is equal to identity map of x. It is well known, or you would have seen earlier, that such maps are precisely the bijective maps from x to x. So I will not get into more into this. Just a comment that if we have a monoid in general, then M cross, this is the set of invertible elements in M. This is in the notation, it is all those x in M such that x is invertible in M. This is a group. M cross with the given binary operation of M is a group, and this group is called unit group of M. It is very important to know the unit group, as you will see in the next example I want to do. For example, if you take the monoid under multiplication, integer, monoid of integers under multiplication, this monoid, obviously you cannot expect the additive identity which we are denoting by 0. This 0 in Z cannot be invertible. With respect to multiplication, of course. So, but even if you remove 0, that is Z minus 0, and this is still a monoid under multiplication. And the only invertible elements, the only invertible element in this monoid in Z minus 0 are plus minus 1. So, the unit group of Z dot this is precisely only plus minus 1, which is too small compared to the set of integers, and that is one of the reasons that we cannot solve the equations like 2 times x plus 1 equal to 0. This is a linear equation with coefficients. So, this is a linear equation with coefficients here are 2 and 1, which are integers, but has no solution in integers. So, that is the reason that we need a system, we need a field which has maximum number of invertible elements with respect to the field, with respect to the multiplication. So, now I will define the concept of field, or first I will define a concept of a ring, and the model example is the set of integers. Set of integers has two operations, plus and multiplication, and what we have noted so far is 1, Z with respect to the operation plus is a commutative group. Sometimes commutative group is also called abelian group. This abelian adjective is attributed to the famous mathematicians Abel. Second property that we observed in this, with respect to multiplication, it is a monoid. And third one, how this plus and multiplication are connected by so called distributive laws. Namely, A times B plus C is same as AB plus AC, and because it is commutative I write only one way. So this is usually called a left distributive law, but our operation is commutative, so I don't want to write it the other way. So this should be called left distributive. So we are interested in the sets which has two binary operations. So more generally, we consider sets with two binary operations. We will denote them by plus and dot, called addition and multiplication. So we are considering the sets R with two binary operation plus and dot. So I will denote this as a triplet satisfying the properties R plus 1 is an abelian group, that means this operation plus is associative, it has the neutral element, and for every element of R there is a inverse with respect to plus. So the neutral element with respect to plus I will keep denoting by 0. When there are more rings under consideration, I will write it 0R. 2 R with multiplication is a commutative monoid. And neutral element of this will be denoted by 1 or 1R. And remember, I am putting this in a definition commutative. So I am defining what is called a commutative ring. If this was not commutative, then one would like to call it a ring in general, but in this course we will never deal with non-commutative rings. We will mostly deal with commutative rings. When we deal with it, I will remind you that now we are considering a non-commutative. Third, the plus and dot, addition and multiplication are connected by distributive laws. A times B plus C equal to AB plus AC for all A, B, C in R. Similarly, one should write A plus B times C equal to AC plus BC. But because the operations are commutative, in our case it is enough to write only one distributive law. So with this, just note that all our standard example, the model example is Z plus dot. This is called a ring of integers. And Q plus dot, R plus dot, C plus dot. This is a commutative ring. Ring of integers is a commutative ring. So all these rational numbers, real numbers, complex numbers with our usual operations of plus and multiplication, they are all commutative rings, but they are more than the commutative rings. Namely, if I take the unit group of the multiplicative monoid of Q Obviously we will have to omit 0 because we have no chance that 0 is invertible with respect to multiplication. So the unit group of rational numbers is all non-zero rational numbers. So if you have a rational number a by b, obviously the inverse of a by b with respect to multiplication will be b by a, and you need non-zeroness because a has to be non-zero to come in the denominator, therefore you need a non-zeroness. Similarly for real numbers, the unit group of non-zero real numbers is precisely all of them, all non-zero real numbers. Similarly for complex numbers. So these are called fields. So field is by definition it's a commutative ring with unit group maximum possible. That is, field is a triplet k plus dot, so it's a commutative ring with the unit group of the multiplicative monoid after omitting 0. This is everybody, all non-zero elements. So all non-zero elements in a field has inverses. We will continue after the break.